Please subscribe to support the channel. The universe has always had a way of humbling us. Every time humanity builds a better telescope, every time we improve our instruments or expand the boundaries of what we can see, the cosmos answers back with something larger, stranger, and more mysterious than we ever expected. It's a reminder that while our planet feels vast, while even our solar system feels enormous, they are merely whispers in the grand conversation of the universe. To start exploring the largest known structure in existence, the Hercules Borealis Great Wall, we must first step back and try to wrap our minds around the sheer scale of the universe itself. When we talk about the universe being vast, that's not a poetic exaggeration. It's a statement of fact that challenges human comprehension. The observable universe stretches about 93 billion light-years across. A light-year, as a unit, is already incomprehensible to many. It's the distance light travels in a single year, moving at about 300,000 kilometers per second. Even our nearest neighboring star, Proxima Centauri, is over 4 light-years away. That means the light we see from it tonight actually left that star more than 4 years ago. Multiply that kind of distance by billions, and you're only just beginning to grasp the dimensions of the observable cosmos. Within this unimaginable expanse are billions of galaxies, each containing billions, even trillions, of stars. Galaxies themselves don't sit in isolation. They cluster together under the invisible glue of gravity, forming structures that are so large, it almost feels wrong to call them objects in the way we might refer to a planet or a star. Instead, they're like patches of fabric in a vast cosmic tapestry. And this tapestry is arranged in a way scientists call the cosmic web, a network of filaments, walls, and clusters, with enormous voids in between that are nearly empty of matter. But before we even get to structures like the Great Wall, let's pause for a moment on scale. To provide a sense of proportion, if our entire solar system were shrunk down to the size of a coin, the Milky Way galaxy would stretch across the size of North America. And yet, even a galaxy as grand as the Milky Way is not the end of the story. Galaxies congregate into groups, those groups assemble into clusters, and those clusters extend into superclusters, which themselves weave together into something even larger. The deeper we look into space, the farther back in time we are also peering. Light takes time to travel, so when we look at distant galaxies, we're seeing them as they were millions or billions of years ago. In this sense, the universe is a time machine, and the scale of what we observe is not just spatial, it is temporal. The Hercules Borealis Great Wall, which we'll explore in detail soon, is so massive and so far away that the light reaching us from it today began its journey billions of years ago, when the universe itself was still young compared to its current age of about 13.8 billion years. The sheer immensity of the cosmos is not just something we know abstractly through science. It has profound implications for how we perceive our place within it. Humanity is a species that has existed for only a blink of an eye in cosmic terms, living on a tiny planet orbiting an unremarkable star in the outskirts of one galaxy among trillions. And yet, through curiosity, observation, and scientific tools, we've managed to chart and measure scales that boggle the imagination. That's both humbling and inspiring. Humbling because of how small we are, inspiring because of how much we've managed to uncover from such a small vantage point. So when we ask, what is the biggest object in the universe? We are really asking about the pinnacle of these structures, the most massive assembly of matter we've detected within the cosmic web. And the answer, for now, is the Hercules Borealis Great Wall. But to fully appreciate its enormity, its significance, and even the controversies surrounding it, we must work our way step by step through the language of cosmic structures, discoveries, and comparisons. Only then can we begin to wrap our minds around what largest really means at a universal scale. When we shift our attention from the broad concept of the universe's scale to the actual structures that inhabit it, we encounter a new vocabulary that astronomers use to make sense of these colossal patterns. It's easy to think about the cosmos as being filled with stars, planets, and maybe the occasional black hole or nebula, but those are the relatively small building blocks. The true giants of the universe are not individual stars, or even single galaxies, they are what scientists call large-scale structures. The phrase large-scale structures refers to the grand architecture of the universe, the interconnected web of galaxies, galaxy clusters, and superclusters that span hundreds of millions to billions of light-years. These structures are held together not by chance, but by the steady pull of gravity, which has been sculpting matter since the very beginning of cosmic time. To grasp this, Think of the universe as a vast 3D network, where galaxies are the glowing nodes, clusters are the thicker intersections, and enormous filaments stretch across space like cosmic highways. Between them lie enormous voids, empty spaces where very little matter exists. Let's break this down further. A galaxy, like our Milky Way, is already an immense city of stars, gas, dust, and dark matter. But galaxies rarely exist alone. They form galaxy groups, such as our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies. These groups then combine into galaxy clusters, which can contain hundreds or thousands of galaxies bound by gravity. Some galaxy clusters are themselves so large and massive that they become gravitational beacons, warping space-time around them in measurable ways. Now scale up again. Clusters do not exist in isolation either. They string together in patterns, forming superclusters, vast assemblies of clusters and groups. Our own galaxy belongs to the Laniakea supercluster, which stretches about 520 million light-years across and includes roughly 100,000 galaxies. It's awe-inspiring to think of our Milky Way as just one tiny member of such a sprawling congregation. But even superclusters are not the end of the story. At the very largest scales, superclusters align in ways that produce immense sheets, walls, and filaments spanning billions of light-years. These are what scientists truly mean by large-scale structures. They are the skeleton of the universe, the framework upon which galaxies and matter are distributed. To an astronomer mapping the cosmos, they look almost like a spider's web, with bright, dense threads of galaxies crisscrossing, leaving vast, empty holes in between. The idea of such structures emerged gradually as technology advanced. Early 20th century astronomers could only see nearby galaxies. It wasn't until the late 20th and early 21st centuries, with large-scale redshift surveys and powerful sky mapping projects, that humanity began to glimpse the universe's true pattern. What they found was shocking. Galaxies were not randomly scattered like dots of paint. Instead, they were organized into enormous, interconnected formations. The universe, in a sense, had structure on the grandest scale imaginable. This discovery was more than just a cartographic achievement. It had profound implications for cosmology, the study of the origin, evolution, and structure of the universe. Scientists realized that these structures were seeded by tiny fluctuations in the density of matter shortly after the Big Bang. Over billions of years, gravity amplified those fluctuations, pulling matter into knots and filaments while leaving voids in between. The result is the cosmic web, which today is considered the largest scale organization of matter in existence. What makes large-scale structures fascinating is that they challenge us to redefine what an object really is. When we call something like the Hercules Corona Borealis Great Wall an object, it's not like a planet you can point to or a star with a clear edge. Instead, it's a massive arrangement of galaxies spanning billions of light-years, connected not by physical bonds but by the invisible threads of gravitational attraction. It's both a structure and a statistical pattern in the distribution of matter, a reflection of the fundamental forces shaping the universe. And here's where things get even more interesting. These structures are so large that they test the limits of one of the core assumptions of cosmology, the cosmological principle, which states that on the largest scales, matter in the universe should be evenly distributed. If you zoom out far enough, in theory, the universe should look smooth and uniform, like a fog. But large-scale structures like galaxy walls and filaments are so enormous that they make us question just how far that principle can be stretched. This transition from galaxies to galaxy groups, to clusters, to superclusters, and finally to walls and filaments prepares us for the star of our story, the Hercules Corona Borealis Great Wall. It is not just another entry in the cosmic catalogue. It is the most extreme example of what a large-scale structure can be, dwarfing everything else we know and stretching our definitions to the breaking point. To understand why it stands out, we first need to explore what it is, where it is located, and how it was discovered. Among all the colossal structures that astronomers have mapped in the cosmic web, one towers above the rest in both scale and reputation: the Hercules Corona Borealis Great Wall. Often shortened simply to the Great Wall in astronomical circles, this entity currently holds the record as the largest known structure in the observable universe. It is not just large by cosmic standards. It is so vast that its existence pushes against the very boundaries of what scientists thought was possible under the current models of cosmology. When we talk about the biggest object in the universe, this is what we mean. It is not a star, not a planet, not even a galaxy or a cluster of galaxies. It is a gigantic wall of galaxies and superclusters spanning distances so immense that even the most gigantic superclusters we know of appear small in comparison. This wall stretches across the cosmos in a way that redefines our sense of scale. To call it the largest known structure is almost underselling it, because the Hercules Corona Borealis Great Wall is the kind of discovery that forces cosmologists to rethink how matter organizes itself at the grandest scales. The name itself hints at its location in the heavens. It lies in the general direction of the constellations Hercules and Corona Borealis, which are part of the northern sky. Astronomers often anchor their discoveries to constellations so that they can be identified and catalogued in relation to familiar sky maps. Just as the Sloan Great Wall takes its name from the survey that discovered it, the Hercules Corona Borealis Great Wall takes its name from the patch of sky where it appears, spanning across two recognizable constellations. The name is functional, but when you grasp its immensity, it feels almost poetic, a great wall on a scale beyond imagination. To give you perspective, other great walls have been identified in cosmic cartography. The CFA-2 Great Wall, discovered in the late 1980s, was the first massive galaxy wall detected, spanning about 500 million light-years. Later, the Sloan Great Wall was discovered, measuring about 1.4 billion light-years across. At the time, it was hailed as one of the largest structures ever seen. But then came the Hercules Corona Borealis Great Wall, and it dwarfed both, clocking in at an incredible 10 billion light-years in length. That number is so staggering it deserves to be repeated. 10 billion light-years. That's more than a tenth of the entire observable universe. The light from one end of this structure to the other would take 10 billion years to cross, which is nearly 3/4 the age of the universe itself. If you set the Milky Way galaxy down next to it, our home galaxy, stretching only about 100,000 light-years across, would look like a single grain of sand at the base of a continent-sized mountain range. What makes the Hercules Corona Borealis Great Wall so significant is not just its size, but the way it challenges our understanding of cosmology. The cosmological principle suggests that on the very largest scales, the universe should be homogeneous and isotropic, meaning it should look roughly the same in all directions. Structures as enormous as this wall raise difficult questions. How can something so vast exist without breaking that rule? Is it truly one single coherent structure, or is it a projection of multiple alignments seen from our perspective? These questions continue to be debated, but regardless of the interpretation, the Hercules Corona Borealis Great Wall has secured its place as the most jaw-dropping of the large-scale structures we've discovered so far. And yet, this massive wall wasn't stumbled upon in a casual star survey. Its discovery came in a rather surprising way, through the study of gamma-ray bursts, the most energetic explosions in the universe. By mapping where these bursts occurred, astronomers revealed a hidden pattern that pointed directly to the existence of the wall. This unexpected route of discovery adds another layer of intrigue to its story, one that we'll dive into after we've situated this structure more clearly in the cosmic sky. When astronomers talk about the Hercules Corona Borealis Great Wall, one of the first things people naturally ask is, where is it? After all, when we hear about something this monumental, the largest known structure in the observable universe, there's an instinct to look up at the night sky and wonder if it's visible to the naked eye. The truth is that while the Great Wall itself is far too distant and diffused to be seen without the most advanced instruments, its position in the sky is linked to two constellations that stargazers have known for centuries: Hercules and Corona Borealis. These constellations are part of the northern celestial hemisphere, visible from much of Earth. The constellation Hercules, as its name suggests, was named after the legendary hero of Greek mythology. It's not one of the brightest constellations, but it's fairly large and contains the famous globular cluster Messier 13, often called the Great Hercules Cluster. To its side sits Corona Borealis, the northern crown. This small but distinctive arc of stars forms a graceful semicircle that has caught the attention of cultures around the world. In Greek mythology, the crown belonged to Ariadne, who was rescued by Dionysus. The Hercules Corona Borealis Great Wall takes its name because it lies in the general direction of these two constellations. Astronomers often use constellations as reference markers to describe the part of the sky where something is found, even though the constellations themselves are just patterns of relatively nearby stars. Imagine standing on Earth and pointing toward a particular patch of sky. That's essentially what astronomers are doing. The wall is not in the constellations in the same way a star or a nebula might be. It is billions of light years beyond them, lurking at an almost unfathomable distance. But from our vantage point, its position lines up with that region of the sky, hence the name. This naming convention is not unusual in astronomy. Other colossal structures are similarly identified based on their position relative to familiar star patterns or surveys. For example, the Sloan Great Wall takes its name from the Sloan Digital Sky Survey, which first mapped it. In the case of the Hercules Corona Borealis Great Wall, the name is both a practical locator and a poetic label. The very words Great Wall evoke something monumental, impenetrable, and awe-inspiring, while tying it to constellations that humans have recognized since antiquity gives it a cultural anchor across thousands of years. Now, if you were to look toward Hercules and Corona Borealis on a clear, dark night, you would see stars only a few hundred or a few thousand light-years away. They sparkle brightly in our sky because they are relatively nearby neighbors in the Milky Way. But the Great Wall sits unimaginably farther away, at distances on the order of 10 billion light-years. That means when we study this structure, we are looking back in time to an era when the universe was less than 5 billion years old. What we see is not the present-day state of the wall, but a snapshot of its distant past, frozen in light that has only just reached us. This location also makes the Great Wall especially fascinating to astronomers because it spans such a massive portion of the sky in that region. If you could overlay a map of the wall on our view of the constellations, it would cover a large area, stretching across the boundaries of multiple constellations and bleeding beyond Hercules and Corona Borealis themselves. This gives you a sense of just how dominant it is as a structure. It's not a pinpoint, not a cluster in one tight spot, but a sprawling feature that sprawls across the cosmos. Understanding its placement is also critical for future observations. When astronomers direct their telescopes toward this region of the sky, they are not simply observing stars in our galaxy. They are peering through those stars into the deep cosmic background, tracing the faint light of galaxies billions of light-years away. It is in this zone that the extraordinary concentration of galaxies and gamma-ray bursts revealed the outline of the Great Wall. The Hercules Corona Borealis Great Wall, therefore, serves as a kind of cosmic backdrop behind the familiar constellations. Its name ties the unimaginable to the familiar, allowing us to connect human traditions of stargazing with discoveries at the very frontier of cosmology. It's like being told that behind a simple crown of stars lies a structure so enormous it makes every story we've ever told about the sky seem small in comparison. And that leads us to an equally important question: how did we even discover something so vast in the first place? The answer lies in an unexpected tool, the study of gamma-ray bursts. In 2013, scientists first identified the Great Wall by noticing patterns in these powerful cosmic explosions, leading to one of the most remarkable discoveries in astronomy. The story of the Hercules Corona Borealis Great Wall's discovery is as fascinating as the structure itself, because it wasn't revealed through the usual painstaking process of mapping galaxies one by one. Instead, it emerged from one of the most energetic and violent phenomena in the cosmos, gamma-ray bursts. These bursts are short-lived but unimaginably powerful flashes of gamma-ray radiation, often caused by the collapse of massive stars into black holes or the collision of neutron stars. For a brief instant, a gamma-ray burst can outshine entire galaxies, releasing more energy in a matter of seconds than our Sun will emit in its entire lifetime. In 2013, a team of astronomers led by Istvan Horvath, John Hackler, and Zsolt Bagely were studying the spatial distribution of gamma-ray bursts detected by satellites like NASA's Swift spacecraft. Gamma-ray bursts are particularly useful for probing the large-scale structure of the universe because they can be seen across incredible distances. They act like cosmic lighthouses, signaling the locations of galaxies and massive events in regions we might otherwise struggle to study. What the team found was unexpected. As they plotted the positions of these gamma-ray bursts on the cosmic map, they noticed a striking clustering pattern. Instead of being randomly scattered, a significant concentration of bursts seemed to be coming from the same vast region of the sky, the direction of the Hercules and Corona Borealis constellations. This wasn't just a handful of bursts clustering together by chance. It was a statistically significant alignment spanning billions of light-years. By carefully analyzing the redshifts, the stretching of light that occurs as the universe expands, the researchers determined that these bursts weren't just happening near each other in our line of sight. They were actually located at roughly the same distance from Earth, about 10 billion light-years away. This indicated that the clustering wasn't a coincidence, but rather a real physical structure, a massive wall of galaxies and galaxy clusters spanning a mind-bending 10 billion light-years across. The announcement of this finding in late 2013 was met with both awe and skepticism. On one hand, the sheer scale of the structure was jaw-dropping. Nothing so large had ever been detected, and it made even previously discovered megastructures, like the Sloan Great Wall or the huge large quasar group, huge LQG, look modest in comparison. On the other hand, some scientists questioned whether the clustering of gamma-ray bursts truly reflected a coherent structure, or if it was an observational artifact. After all, gamma-ray bursts are rare and unpredictable, and relying on them to map cosmic structures is not as straightforward as traditional galaxy surveys. Still, the evidence was strong enough to suggest that this was more than a fluke. The Hercules Corona Borealis Great Wall had entered the record books as the largest known structure in the observable universe. Its discovery highlighted the creative ways astronomers push the boundaries of our knowledge. Instead of relying solely on galaxy surveys, they used some of the universe's most violent explosions as traces of cosmic geography. It was a reminder that science often advances not just through the expected methods, but through unexpected clues that point towards something much larger than anticipated. The discovery also reignited discussions about the limits of the cosmological principle. If the universe is supposed to look roughly uniform on the largest scales, how can a structure spanning 10 billion light-years exist? The Great Wall was so large that it seemed to challenge our very understanding of how matter is distributed across the cosmos. Some astronomers proposed that it might not be a single structure at all, but a statistical alignment of smaller structures that only appeared as one giant wall from our perspective. Others argued that if it was real, it meant we might need to revise our assumptions about the universe's large-scale uniformity. Despite these debates, the discovery of the Hercules Corona Borealis Great Wall marked a turning point. It showed that even in the 21st century, when we think we've mapped and measured almost everything observable, the universe still has surprises that can rewrite our textbooks. It also reinforced the role of gamma-ray bursts as invaluable tools for exploring the distant cosmos. Bursts of light from dying stars that illuminate not just their host galaxies, but entire structures billions of light-years away. And so, with its discovery, the Hercules Corona Borealis Great Wall went from being a hidden, invisible giant lurking in the cosmic web to the crown jewel of large-scale structures. But to truly appreciate just how overwhelming this wall is, we need to pause and talk about its scale. Numbers alone hardly do it justice, but by breaking down its size and comparing it to things we're more familiar with, we can begin to get a faint sense of just how staggering it really is. The size of the Hercules Corona Borealis Great Wall is perhaps the single most astonishing aspect of this cosmic behemoth. When astronomers describe it as roughly 10 billion light-years across, it's difficult for the human mind to truly grasp what that means. To put it in perspective, a light-year is the distance light travels in 1 year, nearly 10 trillion kilometers, or about 6 trillion miles. Multiply that by 10 billion, and you are dealing with distances so immense that conventional comparisons fail. This is not just larger than galaxies, clusters, or even superclusters. It is larger than anything previously imagined in the observable universe. To understand the scale, let's start smaller and build up. Our home galaxy, the Milky Way, stretches about 100,000 light-years across. That's already incomprehensibly vast in human terms, spanning billions of times the distance between Earth and the Sun. Yet, when you place the Milky Way next to the Great Wall, it is almost invisible, like a single pixel on an image covering an entire continent. The Hercules Corona Borealis Great Wall is roughly 100,000 times wider than the Milky Way. If our galaxy was shrunk to the size of a coin, the Great Wall would stretch across the entire North American continent, and then some. Even compared to other known large-scale structures, the Great Wall's enormity is unmatched. The Sloan Great Wall, which was once celebrated as one of the largest formations, spans about 1.4 billion light-years, roughly 1/7 the size of the Hercules Corona Borealis Great Wall. The huge LQG, large quasar group, measures about 4 billion light-years across, which is still less than half the length of the Great Wall. This makes the Hercules Corona Borealis Great Wall not just the largest wall we know of, but the largest coherent structure ever detected in the observable universe. Its sheer length is mind-boggling, covering a distance so vast that light itself would require a quarter of the age of the universe just to travel from one end to the other. Visualizing it in a more concrete way can help, even if only slightly. If we imagine our Milky Way as a single point of light, the Great Wall is a sprawling web of points, countless galaxies, stretching across a staggering fraction of the observable cosmos. In terms of volume, the wall contains hundreds of thousands of galaxies, each with billions of stars, bound together in an intricate network of filaments. Its mass is equally monumental, although difficult to calculate precisely. Astronomers estimate that the combined gravitational pull of this structure is tremendous, shaping the motion of galaxies within and around it, even over billions of light-years. The Great Wall scale also emphasizes how much of the universe remains invisible to us. The observable universe is about 93 billion light-years across. That means this single structure occupies more than 10% of the observable cosmos in length alone, stretching across such an enormous distance that it seems to defy the expectation that the universe becomes uniform on the largest scales. When scientists discovered the wall, it was such an unprecedented find that it immediately sparked debates about the limits of structure formation in the universe. According to conventional cosmology, matter should appear roughly uniform at scales above 1.2 billion light-years. Yet here is a structure nearly 10 times that size, suggesting that the cosmos is more complex than simple models had predicted. Another way to appreciate its scale is to think in terms of time. Because it is 10 billion light-years away, the light we see from it today began its journey 10 billion years ago, when the universe was less than 4 billion years old, roughly a third of its current age. Observing the Great Wall is therefore not just a matter of seeing something far away. It is looking back into the distant past, witnessing a structure as it existed when galaxies and stars were still maturing. Every photon we detect from this wall carries a story from a universe that was younger, smaller, and yet already forming patterns on a scale that boggles the mind. Its sheer enormity also challenges human intuition. In our everyday lives, we are accustomed to measuring distances in kilometers, miles, or even astronomical units. A single structure stretching 10 billion light-years simply cannot be comprehended with these units. Even imagining traveling across it at the speed of light, the ultimate cosmic speed limit, would take 10 billion years, far exceeding the lifetime of every civilization that has ever existed on Earth. It's the kind of scale that makes even cosmologists pause in awe, as it highlights how insignificant a single planet, a single star, or even a single galaxy is when compared to the grandeur of the universe. Yet despite its size, the Great Wall is not solid or continuous in the way we might imagine a terrestrial wall. It's composed of galaxy clusters and filaments linked by gravity, forming a network that resembles a web rather than a monolithic object. Vast voids, regions of space containing very little matter, lie between its filaments, meaning that although it stretches across 10 billion light-years, much of that space is relatively empty. This combination of immense scale and intricate structure is what makes the Hercules Borealis Great Wall so fascinating. It is simultaneously colossal and delicate, massive yet intricately woven. Understanding the scale of the Great Wall also provides perspective on how small our solar system, our galaxy, and even our local supercluster are in the grand scheme. We are living on a planet orbiting a modest star in a galaxy tucked into the outskirts of a supercluster. And yet, by observing cosmic phenomena, we can detect and measure structures billions of times larger than ourselves. This ability to detect such immense structures underscores the extraordinary power of modern astronomy and the ingenuity of human curiosity. The enormity of the Hercules Borealis Great Wall is therefore not just a matter of numbers. It is a testament to the universe's boundless scale, a scale that dwarfs everything we know, challenges our models of cosmic uniformity, and forces us to confront our own smallness. In the next step, we can better appreciate its enormity by comparing it directly to the Milky Way, which offers a more tangible frame of reference for just how colossal this structure really is. To truly grasp the immensity of the Hercules Borealis Great Wall, it helps to put it side by side with something familiar, our own galaxy, the Milky Way. The Milky Way is already an enormous structure in human terms. It's a sprawling spiral galaxy containing roughly 100 billion stars, vast clouds of gas and dust, and dark matter that binds it all together. It spans about 100,000 light-years across, which, on a cosmic scale, is relatively modest. Even light, traveling at its unimaginable speed of 300,000 kilometers per second, takes 100,000 years to cross it from one edge to the other. For a galaxy, that's large, but it's still microscopic when compared to structures like the Hercules Borealis Great Wall. If we place the Milky Way next to the Great Wall, the difference is staggering. The Great Wall stretches roughly 10 billion light-years across, which is 100,000 times the width of our galaxy. To put that in another perspective, if the Milky Way were shrunk down to the size of a small coin, the Great Wall would stretch across an entire continent and beyond. That kind of comparison is almost meaningless in everyday terms because our brains simply cannot process distances on that scale. It's not just a matter of size, it's a question of cosmic perspective. The contrast also highlights just how small and localized our home galaxy is in the universe. We often think of the Milky Way as the galactic neighborhood, and in terms of our immediate cosmic environment, it is. But in the grand tapestry of the universe, the Milky Way is a tiny filament in a web that stretches billions of light-years. The Hercules Borealis Great Wall contains hundreds of thousands of galaxies, each comparable to or larger than the Milky Way itself. In essence, our galaxy is a single thread in an immense cosmic fabric. Another striking way to appreciate the difference is in terms of time. The Milky Way has taken billions of years to form its structure of spiral arms, stars, and clusters. Yet the Great Wall spans distances so vast that it effectively captures the evolution of the universe over billions of light-years of space simultaneously. When we observe one end of the wall, the light reaching us left that region of the universe billions of years ago. Observing the opposite end shows us a different part of cosmic history, essentially allowing astronomers to witness the formation and distribution of galaxies on scales that dwarf individual galactic evolution. Even in terms of mass, the contrast is remarkable. While the Milky Way has a mass estimated around 1.5 trillion solar masses, the Hercules Borealis Great Wall encompasses the combined mass of hundreds of thousands of galaxies. The gravitational influence of such a structure spans an enormous region of space, subtly affecting the motion of galaxies even tens or hundreds of millions of light-years away. While our Milky Way shapes the orbits of its nearby stars and satellite galaxies, the Great Wall's gravitational pull operates on a scale that affects superclusters themselves. This comparison also helps us understand why the discovery of the Great Wall was so shocking to astronomers. According to the cosmological principle, the universe should appear roughly uniform when viewed on sufficiently large scales, with no preferred directions or giant structures exceeding about 1.2 billion light-years. Yet here is a structure that is 10 billion light-years long, nearly 10 times larger than the supposed limit for cosmic homogeneity. The Milky Way, tiny in comparison, sits as a humble observer in a universe far more structured than our intuition would suggest. When thinking about scale, it's almost impossible not to feel a sense of humility. Our entire solar system, planets, moons, asteroids, and comets, is a minuscule fraction of the Milky Way. The Milky Way itself is a fraction of a supercluster. And superclusters, when linked together into filaments and walls like the Hercules Borealis Great Wall, become nearly incomprehensible in magnitude. The comparison makes it clear that even a galaxy as magnificent and vast as the Milky Way is essentially an infinitesimal component of a much grander architecture, one that challenges human perception and forces us to rethink our place in the universe. Moreover, this contrast is not just a numerical exercise. It illustrates why studying large-scale structures matters. By comparing the scale of our own galaxy to these enormous formations, astronomers can better understand how matter clusters under gravity, how cosmic structures evolve over time, and how our local environment fits into the broader cosmic web. Without placing the Milky Way in this context, the concept of the Great Wall would remain abstract, a series of numbers too vast to internalize. But by using the Milky Way as a frame of reference, we can at least begin to glimpse the truly colossal nature of this cosmic wall. In short, the Hercules Borealis Great Wall doesn't just dwarf the Milky Way. It redefines scale itself, showing us that our galaxy, while massive on human terms, is only a tiny thread in a structure so large that light takes billions of years to traverse it. The comparison also sets the stage for understanding how this wall relates to other cosmic megastructures, which, while enormous, are still far smaller than this record holder. To truly appreciate the Hercules Borealis Great Wall, it helps to compare it to other enormous structures that populate the cosmic web. While the universe is filled with clusters, superclusters, and filaments, only a handful qualify as megastructures, structures that stretch across immense stretches of space and dwarf entire galaxies. Two of the most well-known of these are the Sloan Great Wall and the Huge Large Quasar Group, Huge LQG, both of which set records in their time before the Great Wall's discovery. The Sloan Great Wall, discovered in 2003, is one of the first giant structures identified in the era of large-scale galaxy surveys. Named after the Sloan Digital Sky Survey, SDSS, this wall of galaxies spans roughly 1.4 billion light-years. That's already almost 14,000 times the diameter of the Milky Way and a scale that boggles the human mind. The Sloan Great Wall is composed of thousands of galaxies organized into clusters and superclusters, forming a filamentary chain that traces the cosmic web. For a decade, it was considered the largest known structure in the universe, a monumental achievement for astronomers mapping the cosmos. Then there is the huge LQG, or Huge Large Quasar Group, discovered in 2012. This structure is approximately 4 billion light-years across, containing a staggering number of quasars, extremely luminous active galactic nuclei powered by supermassive black holes. Quasars are incredibly useful as tracers of large-scale structure because they are bright enough to be observed across billions of light-years. The huge LQG, therefore, revealed a concentration of matter on a scale previously thought to challenge the cosmological principle. Although smaller than the Sloan Great Wall in length, the huge LQG is remarkable for its density of quasars, highlighting that large-scale structures can take various forms, not just walls of galaxies but also networks of highly energetic galactic nuclei. Even compared to these giants, the Hercules Corona Borealis Great Wall far surpasses them in sheer size, stretching roughly 10 billion light-years across. That's nearly 7 times the length of the Sloan Great Wall and more than double the size of the huge LQG. In terms of cosmic hierarchy, it is the undisputed champion of scale, the largest known coherent structure in the observable universe. While other walls and large quasar groups capture the imagination because of their extremity, the Great Wall pushes the envelope to a point where conventional cosmological models begin to strain under its enormity. Part of what makes the Great Wall so extraordinary in comparison is not just its length, but also its implications for cosmic uniformity. Cosmologists expect that at scales larger than roughly 1.2 billion light-years, the universe should appear roughly uniform and isotropic. The Sloan Great Wall, at 1.4 billion light-years, already approaches that threshold, suggesting the universe is structured in ways that barely push against expectations. The huge LQG, at 4 billion light-years, raises the stakes even higher. Yet the Hercules Corona Borealis Great Wall, at 10 billion light-years, dramatically exceeds this scale, prompting questions about whether our assumptions about homogeneity need to be revisited. In other words, while previous megastructures were remarkable, this wall forces astronomers to reconsider the upper limits of cosmic structure formation. Another point of comparison is the composition and connectivity of these structures. The Sloan Great Wall is primarily a network of galaxy clusters, with dense regions punctuated by voids. The huge LQG, by contrast, is defined by quasars, which are rarer and more energetic than typical galaxies. The Hercules Corona Borealis Great Wall combines elements of both. It is a network of galaxy clusters, superclusters, and filaments, forming a continuous wall-like pattern across the sky. Its size and complexity make it a richer, more intricate example of a cosmic megastructure. It is not just long, it is densely interconnected, with strands of galaxies tracing a web that is both vast and coherent. The comparison also underscores how the discovery methods differ. The Sloan Great Wall was mapped using traditional galaxy redshift surveys, measuring the positions of thousands of galaxies in three-dimensional space. The huge LQG relied on the positions of luminous quasars to trace an immense structure indirectly. The Hercules Corona Borealis Great Wall, however, was revealed primarily through gamma-ray bursts, which are far rarer events. This means that while other structures were identified using more conventional surveys, the Great Wall's detection depended on innovative techniques, highlighting how astronomers can discover even larger structures by looking in unconventional ways. By placing the Hercules Corona Borealis Great Wall alongside these other megastructures, the scale of the universe becomes almost incomprehensible. The Milky Way is a tiny spiral in the cosmic ocean. The Sloan Great Wall and huge LQG are enormous continental landmasses, stretching across space in ways our brains struggle to imagine. And the Hercules Corona Borealis Great Wall? It is an entire supercontinent spanning billions of light-years, dominating the cosmic landscape and redefining the very notion of largest. In summary, the Great Wall is not just bigger, it is orders of magnitude beyond what came before. It dwarfs previous record holders in length, complexity, and scale, solidifying its status as the largest known structure in the observable universe. Its size challenges our understanding of cosmic structure, its discovery pushes the boundaries of observational methods, and its existence forces scientists to reconsider the limits of cosmic uniformity. When compared to other megastructures, the Great Wall is not merely the biggest, it is a monument to the universe's capacity for scale, complexity, and wonder. The Hercules Borealis Great Wall is not a single object in the traditional sense. Unlike a star, a planet, or even a galaxy, which has relatively well-defined boundaries, this colossal wall is best understood as a massive network of galaxy clusters and superclusters bound together by gravity. It is a sprawling, interconnected structure, a kind of cosmic tapestry in which the threads are galaxies and the knots are clusters, stretching across billions of light-years. At its core, the Great Wall is composed of thousands of galaxies, each of which contains billions of stars. These galaxies are grouped into clusters, which themselves are gravitationally bound collections of galaxies that interact over cosmic timescales. Galaxy clusters are not uniform. Some contain dense cores with tightly packed galaxies, while others are more diffuse, with galaxies scattered over vast regions. Within the Great Wall, these clusters are strung together in filaments, creating elongated structures that trace the shape of the wall across space. These filaments are a hallmark of the cosmic web, the large-scale structure of the universe. In this web, matter is not evenly distributed. Instead, it forms dense regions where galaxies cluster and vast voids where very little matter exists. The Great Wall occupies one of these dense regions, forming a coherent network of filaments that stretches across an almost incomprehensible distance. Between these filaments, the voids may span hundreds of millions of light-years, giving the Great Wall a structure that resembles a giant cosmic mesh more than a solid, continuous object. The wall is also composed of superclusters, which are collections of galaxy clusters bound loosely by gravity. Superclusters themselves can span hundreds of millions of light-years, making them enormous on their own. When superclusters align or connect via filaments, as they do in the Great Wall, they create structures so large that light takes billions of years to traverse them. The wall is, therefore, a hierarchical structure. Individual galaxies form clusters, clusters form superclusters, and superclusters form walls and filaments. This hierarchical nature is fundamental to the way the universe organizes itself at the largest scales. Gravity is the invisible glue holding it all together. Although the galaxies within the wall are separated by immense distances, their mutual gravitational attraction ensures that they are not just a random collection. They form a coherent pattern, moving in subtle ways that reflect the distribution of mass throughout the structure. Dark matter, which makes up most of the universe's mass, also plays a critical role in shaping the wall. While invisible to telescopes, dark matter provides the gravitational scaffolding on which galaxies and clusters assemble. Without it, the Hercules Borealis Great Wall, and indeed all large-scale structures in the universe, would not have formed in the same way. It is important to note that, despite its vastness, the Great Wall is not a single, solid object in a conventional sense. There are enormous gaps between the filaments, and galaxies within the wall are not physically touching each other. The structure is defined by gravitational relationships and spatial patterns, not by continuity or solidity. In other words, it is a statistical and physical phenomenon, identified through careful mapping of galaxies and cosmic events, rather than a monolithic entity. This composition also helps explain why gamma-ray bursts were crucial for its discovery. Since the wall is spread across such a large distance, individual galaxies are faint and difficult to detect in traditional surveys. Gamma-ray bursts act as beacons, revealing the locations of galaxies across vast stretches of space. By mapping these bursts and correlating them with redshift measurements, astronomers could trace the outlines of the wall, revealing its network-like structure of clusters and filaments. In addition to galaxies and superclusters, the wall contains enormous amounts of intergalactic gas. This gas, primarily hydrogen and helium, threads between galaxies and clusters, contributing to the overall mass and gravitational pull of the structure. While largely invisible in optical wavelengths, this gas can be detected through X-ray and radio observations, and it plays a key role in the formation of new stars and galaxies within the wall over cosmic timescales. The composition of the Hercules Borealis Great Wall illustrates the complexity of cosmic architecture. Unlike a solid object, Its boundaries are fluid and defined more by patterns than by edges. It is a dynamic system, with galaxies moving within clusters, clusters drifting relative to each other, and filaments evolving under the influence of gravity and dark matter. The wall is a snapshot of the universe's large-scale structure, capturing billions of years of cosmic evolution frozen in space and time. Understanding what it's made of also emphasizes why the Hercules Corona Borealis Great Wall is so different from smaller structures. While galaxies, clusters, and even superclusters are massive in their own right, the wall represents an assembly of assemblies, a network of networks, which magnifies its scale and significance. Its size, composition, and coherence make it a landmark of the universe, a testament to the gravitational forces shaping the cosmos over billions of years. By looking at its composition, we also begin to see why such structures were only discovered relatively recently. Mapping individual galaxies is one thing, but tracing a coherent structure across billions of light-years requires precise measurements and innovative techniques, like using gamma-ray bursts as cosmic signposts. Without understanding the networked nature of the wall, that it is made of clusters and filaments rather than a single, monolithic body, it would be impossible to appreciate its true scale and significance. The discovery of the Hercules Corona Borealis Great Wall relied on an unexpected and extraordinary cosmic tool, gamma-ray bursts, GRBs. These are not your everyday astronomical events. GRBs are among the most energetic explosions in the universe, outshining entire galaxies for a brief moment. They typically occur when massive stars reach the end of their lives and collapse into black holes, or when two neutron stars collide. In either case, the result is an enormous release of energy in the form of gamma radiation, often lasting from a fraction of a second to several minutes. For that short time, a single GRB can emit more energy than the Sun will over its entire 10 billion-year lifetime. The sheer brilliance of gamma-ray bursts makes them extremely useful to astronomers. Because they are so luminous, they can be observed across billions of light-years, far beyond the reach of traditional galaxy surveys. In this sense, GRBs act as cosmic lighthouses, signaling the locations of galaxies in regions of the universe that are otherwise difficult to study. While we cannot see the individual galaxies in these distant regions as clearly as we can nearby galaxies, we can detect the bursts themselves and use their positions to map the underlying distribution of matter. In 2013, a team of astronomers led by Istvan Horvath, John Hackler, and Zsolt Bagely analyzed the spatial distribution of GRBs detected by satellites such as NASA's SWIFT and the European Space Agency's Integral. They plotted hundreds of GRBs across the sky and looked for patterns in both their positions and their redshifts, which measure how much the universe has expanded since the light left the source. Redshift allows scientists to estimate the distance to each burst and, consequently, to infer its location in three-dimensional space. What they found was startling. A large number of GRBs were not randomly distributed, as one would expect if the universe were completely uniform on large scales. Instead, these bursts appeared to cluster in a specific region of the sky, the direction of the Hercules and Corona Borealis constellations, and at roughly the same cosmic distance, about 10 billion light-years away. This clustering suggested the presence of a massive underlying structure, a wall-like network of galaxies and galaxy clusters spanning billions of light-years. By connecting the dots provided by these GRBs, astronomers could effectively outline the shape and scale of the Hercules Corona Borealis Great Wall. Using GRBs in this way was particularly innovative because traditional methods of mapping large-scale structures, such as counting galaxies in redshift surveys, become increasingly difficult at extreme distances. Galaxies billions of light-years away are faint and often too small to be individually resolved. Gamma-ray bursts, however, are so bright that they can be detected across the entire observable universe, making them perfect tracers for distant cosmic structures. Each GRB serves as a marker for the location of its host galaxy, and by mapping these markers collectively, astronomers can reveal the contours of structures far larger than any individual galaxy survey could detect. The process works because GRBs are associated with star-forming galaxies, which are not evenly distributed. When GRBs cluster in both position and redshift, it indicates that their host galaxies are also clustered, forming filaments, walls, and superclusters. In essence, the bursts act like pinpoints of light in a vast dark web, revealing the skeleton of the universe on scales that would otherwise be invisible. This is exactly how the Hercules Corona Borealis Great Wall was brought into focus. By tracing patterns in rare, transient, and extremely energetic events, astronomers were able to detect the largest known structure in the universe. It's also worth noting that this method adds temporal depth to the discovery. Because light takes billions of years to reach us from such distances, each GRB is a glimpse back in time. The clustering of these bursts shows that the Great Wall existed 10 billion years ago, when the universe was much younger. This means that the structure we see is a historical snapshot, capturing the distribution of galaxies and clusters at a formative stage of cosmic evolution. Without gamma-ray bursts acting as markers, it would be nearly impossible to detect such a remote structure and understand its scale. The use of GRBs to map the wall also emphasizes the ingenuity of astronomers in leveraging every available tool to study the universe. Unlike ordinary surveys, which require visible light or other electromagnetic observations, GRBs provide a direct probe into the distant, high-energy universe. By charting these cosmic explosions, scientists effectively lit up a region of the sky that revealed the hidden web of matter stretching across billions of light-years. In short, gamma-ray bursts were the cosmic breadcrumbs that led to the discovery of the Hercules Corona Borealis Great Wall. These violent, fleeting explosions trace the distribution of galaxies across an almost unimaginable distance, revealing a wall-like structure that dwarfs everything else in the observable universe. Without GRBs, the largest known structure in the cosmos might have remained hidden, its existence unknowable from our small vantage point on Earth. The term wall in the context of the Hercules Corona Borealis Great Wall might evoke an image of a solid, physical barrier stretching across the cosmos, but in reality, it refers to the appearance and arrangement of matter on a grand scale. Astronomers use this terminology to describe how galaxies and galaxy clusters organize themselves in space. Dense, elongated structures interwoven across vast regions, with immense voids of near-empty space separating them. To understand this, imagine a cosmic web. In this web, galaxies are not uniformly distributed. Instead, they collect along filaments, long, thread-like chains of matter. These filaments connect galaxy clusters and superclusters, forming intersections and networks. In regions where filaments converge, you find dense collections of galaxies, whereas the spaces between filaments are cosmic voids, vast expanses containing very little matter. A wall is essentially a high-density filament that stretches across immense distances, giving the impression of a continuous sheet or boundary when mapped in three-dimensional space. The Hercules Corona Borealis Great Wall is a textbook example of such a formation. Observations show that it consists of numerous galaxy clusters and superclusters linked along elongated filaments, stretching roughly 10 billion light-years across. Between these filaments lie enormous voids, sometimes hundreds of millions of light-years wide, creating a pattern reminiscent of threads of cotton candy separated by empty space. The wall terminology helps astronomers visualize the linear, planar structure that arises from this arrangement. It is not a literal wall like one might encounter on Earth, but a descriptive term that conveys the scale, shape, and density of the formation. This concept is not unique to the Hercules Corona Borealis Great Wall. Other large-scale structures, such as the Sloan Great Wall or the CFA2 Great Wall, were also named for their apparent wall-like alignment of galaxies. In each case, what astronomers observed was a coherent sheet or filament of galaxies that stood out against the surrounding, less dense cosmic regions. In the Great Wall's case, the term wall captures the sheer magnitude of the structure and its distinctiveness in the cosmic web, a formation so massive that it stretches across an unprecedented portion of the observable universe. One way to visualize it is to imagine a three-dimensional map of galaxies in a section of space. If plotted on a graph, the galaxies do not scatter evenly like grains of sand. Instead, they form lines, sheets, and knots. Some of these sheets are relatively thin but incredibly long, forming what appears to be a wall. The Hercules Corona Borealis Great Wall is the largest of these sheets, stretching across a significant fraction of the observable cosmos. When seen from Earth's perspective, it aligns with a specific portion of the sky, giving the impression of a continuous, planar structure, even though it is composed of discrete clusters connected by filaments of galaxies. The wall terminology also emphasizes the contrast with the surrounding voids. Cosmic voids are regions of space with far fewer galaxies than average, sometimes appearing as immense empty bubbles in the universe. The Great Wall, by contrast, is a region of extraordinary galaxy density. Its wall-like appearance is therefore defined not just by the galaxies it contains but by the empty spaces that frame it, which highlight its linear and sheet-like nature. In essence, the wall is made visible by the juxtaposition with near-empty regions of space. Additionally, walls are sometimes described as filaments on an extreme scale. Filaments are the most common form of large-scale structure in the cosmic web, but when multiple filaments align or merge over billions of light-years, they take on the appearance of a wall. The Hercules Corona Borealis Great Wall is exactly this, a collection of aligned filaments forming a continuous, high-density structure that spans a vast portion of the universe. The term wall therefore conveys both linear continuity and structural coherence, distinguishing it from isolated clusters or smaller networks. The name also helps to communicate scale to the public. When scientists describe the Sloan Great Wall or the Hercules Corona Borealis Great Wall, the word wall instantly suggests something immense and imposing, which is accurate in a cosmic sense. While the wall is not physically solid, it is an extreme example of the universe's hierarchical organization. Galaxies forming clusters, clusters forming superclusters, and superclusters forming sheets and filaments that stretch across billions of light-years. In summary, the Hercules Corona Borealis Great Wall earns its name because it is a coherent, planar concentration of galaxies, stretching across the sky in a manner that visually and structurally resembles a wall. It highlights the density of matter in that region of space, the connections between galaxy clusters and superclusters, and the immense voids that separate it from less populated regions. This wall-like formation is one of the clearest and most extreme examples of the cosmic web in action, demonstrating the universe's ability to organize matter into structures that defy human comprehension. The discovery of the Hercules Corona Borealis Great Wall was not just a triumph of observational astronomy, it also posed a profound challenge to our understanding of the universe itself. One of the foundational assumptions in cosmology is the cosmological principle, which states that, on sufficiently large scales, the universe is homogeneous and isotropic. In simpler terms, no matter where you look in the cosmos, matter should be distributed roughly evenly, and the universe should look the same in all directions. This principle underpins almost every modern model of cosmic evolution, from the Big Bang to the formation of galaxies and superclusters. Yet the Hercules Corona Borealis Great Wall complicates this picture. Its sheer size, approximately 10 billion light-years across, far exceeds the scale at which the universe was expected to become uniform. Most cosmologists had predicted that beyond roughly 1.2 billion light-years, matter would average out and no structures would dominate. The Great Wall is almost 10 times that scale, stretching across a portion of the observable universe that should, according to the cosmological principle, appear roughly homogeneous. Its existence raises fundamental questions. How can a structure so enormous form in a universe that should be uniform at these scales? This tension is not just theoretical. It has practical implications for cosmology. The standard cosmological models, particularly those based on the lambda cold dark matter paradigm, rely on the assumption that large-scale structure grows from tiny fluctuations in the early universe. Over billions of years, gravity amplifies these fluctuations, forming galaxies, clusters, and superclusters. But structures on the scale of the Hercules Corona Borealis Great Wall stretch the limits of what these models predict. If the wall is truly coherent and continuous, it implies that matter can clump together on scales far larger than previously thought possible, potentially requiring revisions to our understanding of cosmic evolution. Some scientists have suggested alternative interpretations to reconcile this observation with the cosmological principle. One possibility is that the wall is not a single coherent structure, but rather a projection of smaller, aligned clusters and filaments along our line of sight. In this scenario, the wall would appear enormous from Earth, but its actual physical continuity might be less extreme. Another hypothesis is that the observed clustering is a statistical anomaly, an outlier in the universe's overall distribution of matter. While these explanations could mitigate the apparent conflict with homogeneity, neither is entirely satisfying, and the debate remains open. The implications of such a structure are far-reaching. If walls like the Hercules Corona Borealis Great Wall are more common than we realize, it may mean that the universe is less uniform on large scales than previously assumed, forcing cosmologists to revisit foundational assumptions. For instance, models of cosmic inflation, the rapid expansion of space in the early universe, are based on the idea that initial fluctuations were small and uniform. A structure of this size suggests that either inflation allowed for much larger initial variations, or that other mechanisms contributed to the formation of extreme structures. Beyond theoretical models, the wall's size also impacts observational cosmology. Surveys that assume uniformity over large scales may underestimate or overestimate certain cosmic parameters if a structure like the Great Wall is included in their data. For example, estimates of dark energy density, galaxy distribution, or cosmic expansion could be skewed if such massive structures are not accounted for. In this sense, the Hercules Corona Borealis Great Wall is not just a curiosity, it's a test case for the limits of cosmological assumptions. At the same time, the wall invites a re-evaluation of what structure really means on the largest scales. Unlike stars or planets, which are compact objects with clear boundaries, a wall is defined by patterns of matter, clusters, filaments, and voids over billions of light-years. Its detection challenges the idea that homogeneity is a simple, easy-to-verify principle. It may be that the universe achieves average uniformity statistically but still allows for extreme local deviations that produce gigantic walls. Understanding where to draw the line between statistical variation and genuine contradiction is an ongoing task for cosmologists. This tension between observation and principle highlights the dynamic nature of scientific understanding. The discovery of the Great Wall exemplifies how new data can challenge long-standing assumptions, forcing researchers to refine models, question biases, and consider alternative explanations. Whether the wall ultimately represents a true anomaly or a hint at previously unknown aspects of cosmic evolution, it serves as a reminder that the universe is far more complex and surprising than even the most sophisticated theories anticipate. Finally, the wall's size also emphasizes our temporal perspective. Because light from the Hercules Corona Borealis Great Wall takes roughly 10 billion years to reach us, we are seeing it as it was in the distant past. This snapshot may capture a period of cosmic evolution when large-scale structures were still forming, providing valuable insight into the processes that shape matter over billions of years. Yet even in this historical context, the wall remains so vast that it challenges expectations, raising profound questions about the limits of uniformity, the nature of cosmic evolution, and the very principles upon which modern cosmology is built. One of the most mind-bending aspects of the Hercules Corona Borealis Great Wall is that when we observe it, we are not seeing the structure as it exists today. Instead, we are looking billions of years into the past, because the light from this distant region of the universe has taken roughly 10 billion years to reach Earth. In other words, astronomers are seeing the Great Wall as it existed when the universe was less than half its current age, a time when galaxies were still forming, stars were young, and cosmic structures were taking shape. This concept, that observing distant objects is equivalent to looking back in time, is central to astronomy. But the scale of the Great Wall makes it especially dramatic. Consider the vast distances involved. The wall spans 10 billion light-years, meaning the photons we detect today left one end of the structure when the universe was approximately 3.8 billion years old. The universe itself is now roughly 13.8 billion years old. What this means is that, even though the Great Wall exists in the present universe, the image we observe is essentially a cosmic time capsule, revealing a historical snapshot of the early universe. This time-traveling aspect is crucial for understanding the formation and evolution of cosmic structures. The Hercules Corona Borealis Great Wall is composed of galaxy clusters and filaments that formed over billions of years, yet the light we detect today shows us the configuration of those galaxies when they were much younger. By analyzing the distribution of galaxies within the wall, astronomers gain insight into how matter clustered and evolved in the early universe. It's as if the Great Wall provides a window into a formative epoch of cosmic history, revealing patterns that help scientists test models of galaxy formation, dark matter distribution, and gravitational interactions on enormous scales. The light travel effect also highlights the incredible scale of the universe. Unlike nearby galaxies or clusters, where the light we see is relatively recent in cosmic terms, the Hercules Corona Borealis Great Wall is so distant that observing it is akin to watching ancient history unfold. The galaxies within it are seen as they were when the universe was still young, smaller, and denser than it is today. Over the billions of years that their light has been traveling toward us, these galaxies have continued to evolve, merging with others, forming stars, and perhaps even altering their positions relative to one another. What we see is a frozen moment in time, capturing a stage in the universe's evolution that predates much of its current large-scale structure. Moreover, the light travel time underscores the staggering size of the wall itself. Because it stretches across 10 billion light-years, even photons traveling from one end of the wall to the other would take billions of years to traverse the distance. Observing the entire structure means piecing together information from multiple regions, each of which represents a slightly different epoch. This adds a temporal dimension to the wall's already immense spatial scale, making it one of the most complex and awe-inspiring objects ever studied. From a human perspective, it's difficult to comprehend the combination of distance and time. Light from the Sun takes roughly 8 minutes to reach Earth, giving us near real-time information about our closest star. Light from the Milky Way center takes about 25,000 years to arrive, allowing us to peer far back in our own galaxy's history. But the Hercules corona Borealis Great Wall stretches billions of light-years, so observing it is like receiving messages from a time when the universe was a fraction of its current size. Every photon carries information not just about location, but about the state of the universe at that ancient moment. This phenomenon also illustrates why studying distant structures is so essential for cosmology. By examining light that has traveled for billions of years, astronomers can trace the evolution of the universe over cosmic time, from its early, relatively uniform state to the complex network of galaxies, filaments, and walls we observe today. The Hercules corona Borealis Great Wall provides a particularly dramatic example, because it is both so enormous and so distant. Its very existence tells us that massive structures had already begun forming when the universe was young, giving crucial evidence about the timing and mechanisms of structure formation. In practical terms, the light travel time also means that studying the Great Wall requires sophisticated instruments capable of detecting faint, ancient signals. Gamma-ray bursts, deep-field galaxy surveys, and redshift measurements are all tools that allow astronomers to interpret this ancient light and reconstruct the wall structure. Each photon is a messenger from the distant past, and by collecting and analyzing countless photons, scientists can create a three-dimensional map of a structure that existed billions of years ago, a feat that underscores both the ingenuity of human observation and the vastness of the cosmos. Ultimately, the light travel aspect of the Hercules corona Borealis Great Wall adds a profound philosophical dimension. When we observe it, we are literally looking back in time, witnessing a part of the universe as it once was, while simultaneously trying to understand how it has evolved into the universe we inhabit today. It is a humbling. Younger. By analyzing the distribution of galaxies within the wall, astronomers gain insight into how matter clustered and evolved in the early universe. It's as if the Great Wall provides a window into a formative epoch of cosmic history, revealing patterns that help scientists test models of galaxy formation, dark matter distribution, and gravitational interactions on enormous scales. The light travel effect also highlights the incredible scale of the universe. Unlike nearby galaxies or clusters, where the light we see is relatively recent in cosmic terms, the Hercules corona Borealis Great Wall is so distant that observing it is akin to watching ancient history unfold. The galaxies within it are seen as they were when the universe was still young, smaller, and denser than it is today. Over the billions of years that their light has been traveling toward us, these galaxies have continued to evolve, merging with others, forming stars, and perhaps even altering their positions relative to one another. What we see is a frozen moment in time, capturing a stage in the universe's evolution that predates much of its current large-scale structure. Moreover, the light travel time underscores the staggering size of the wall itself. Because it stretches across 10 billion light-years, even photons traveling from one end of the wall to the other would take billions of years to traverse the distance. Observing the entire structure means piecing together information from multiple regions, each of which represents a slightly different epoch. This adds a temporal dimension to the wall's already immense spatial scale, making it one of the most complex and awe-inspiring objects ever studied. From a human perspective, it's difficult to comprehend the combination of distance and time. Light from the Sun takes roughly 8 minutes to reach Earth, giving us near real-time information about our closest star. Light from the Milky Way center takes about 25,000 years to arrive, allowing us to peer far back in our own galaxy's history. But the Hercules corona Borealis Great Wall stretches billions of light-years, so observing it is like receiving messages from a time when the universe was a fraction of its current size. Every photon carries information not just about location, but about the state of the universe at that ancient moment. This phenomenon also illustrates why studying distant structures is so essential for cosmology. By examining light that has traveled for billions of years, astronomers can trace the evolution of the universe over cosmic time, from its early, relatively uniform state to the complex network of galaxies, filaments, and walls we observe today. The Hercules Borealis Great Wall provides a particularly dramatic example, because it is both so enormous and so distant. Its very existence tells us that massive structures had already begun forming when the universe was young, giving crucial evidence about the timing and mechanisms of structure formation. In practical terms, the light travel time also means that studying the Great Wall requires sophisticated instruments capable of detecting faint, ancient signals. Gamma-ray bursts, deep-field galaxy surveys, and redshift measurements are all tools that allow astronomers to interpret this ancient light and reconstruct the wall structure. Each photon is a messenger from the distant past, and by collecting and analyzing countless photons, scientists can create a three-dimensional map of a structure that existed billions of years ago, a feat that underscores both the ingenuity of human observation and the vastness of the cosmos. Ultimately, the light travel aspect of the Hercules Borealis Great Wall adds a profound philosophical dimension. When we observe it, we are literally looking back in time, witnessing a part of the universe as it once was, while simultaneously trying to understand how it has evolved into the universe we inhabit today. It is a humbling reminder that the universe is not static, that light takes time to reach us, and that our understanding of cosmic structures is always a window into the distant past. Mapping a structure as vast as the Hercules Borealis Great Wall is no simple task. The scale, distance, and diffuse nature of galaxy filaments make traditional observational techniques inadequate on their own. Instead, astronomers rely on a combination of innovative tools and methods that allow them to reconstruct the three-dimensional distribution of matter across billions of light-years. Two of the most important techniques are redshift surveys and gamma-ray burst mapping, each contributing complementary insights into the Great Wall structure. Redshift surveys are the cornerstone of large-scale cosmic mapping. The principle is deceptively simple. Light from galaxies is stretched to longer wavelengths as the universe expands, a phenomenon known as the redshift. The more distant a galaxy is, the greater its redshift. By measuring the redshift of thousands, or even millions, of galaxies, astronomers can calculate their approximate distances from Earth. When combined with the galaxy's position on the sky, these distances allow the construction of a three-dimensional map of the galaxy's location in space. This method has been employed in landmark surveys such as the Sloan Digital Sky Survey, SDSS, which revealed structures like the Sloan Great Wall and provided a model for understanding cosmic filaments and voids. For the Hercules Borealis Great Wall, redshift surveys alone are insufficient. The galaxies within this structure are so distant and faint that detecting them individually requires enormous amounts of telescope time and extremely sensitive instruments. At 10 billion light-years away, even massive galaxies appear as tiny, faint smudges. To overcome this, astronomers use statistical techniques. Instead of mapping every single galaxy, they trace indicators of galaxy presence, such as clusters, quasars, or high-energy events like gamma-ray bursts. By combining these data with limited direct galaxy observations, they can infer the overall pattern of matter distribution and reveal the contours of gigantic structures like the Great Wall. Gamma-ray burst mapping, which played a crucial role in discovering the Hercules Borealis Great Wall, offers a different approach. Gamma-ray bursts are short-lived but extraordinarily bright explosions, detectable across billions of light-years. Each burst originates from a host galaxy, and its redshift can be measured to determine distance. By plotting the positions of hundreds of these bursts in both sky coordinates and redshift, astronomers can identify clustering patterns indicative of large-scale structures. This method was particularly effective for the Great Wall because the bursts illuminated regions that were otherwise too distant and faint to map directly. In essence, GRBs act as cosmic beacons, signaling the locations of galaxy clusters and filaments across the early universe. These two methods are often used in tandem. Redshift surveys provide precise measurements of galaxy positions where possible, while gamma-ray bursts fill in the gaps at extreme distances. Additional techniques, such as X-ray observations of galaxy clusters and radio surveys of intergalactic gas, can further refine the map by tracing the mass and structure that are not visible in optical light. The combination of these techniques allows astronomers to reconstruct a three-dimensional representation of the Great Wall, showing not just its position, but its intricate network of filaments, clusters, and voids. Mapping such structures is not only about plotting points in space, it also involves statistical and computational analysis. Researchers must differentiate between Random clustering and genuine large-scale structures account for observational biases and model the influence of cosmic expansion on light travel. Advanced algorithms and simulations are used to verify whether observed patterns are statistically significant or could arise by chance. For the Hercules Corona Borealis Great Wall, the clustering of gamma-ray bursts passed these rigorous tests, confirming that the wall is likely a real, coherent feature of the universe, rather than a coincidental alignment of distant galaxies. Another important aspect of mapping is considering the cosmic web's hierarchical nature. Structures exist on multiple scales, from individual galaxies to clusters, superclusters, filaments, and finally walls. Accurate mapping requires resolving this hierarchy and understanding how smaller structures combine to form larger ones. By analyzing both the positions and densities of galaxies, clusters, and bursts, astronomers can identify the filaments that define the Great Wall and distinguish it from other surrounding structures. The ability to map such enormous structures is a testament to the ingenuity of modern astronomy. It combines decades of observational data, cutting-edge instruments, and sophisticated computational methods to transform faint signals from the distant universe into detailed three-dimensional models. Through these techniques, what was once an invisible arrangement of galaxies billions of light-years away becomes a tangible map, revealing the structure, scale, and complexity of the largest known formation in the cosmos. In short, redshift surveys and gamma-ray burst mapping are complementary tools that allow astronomers to chart the Hercules Corona Borealis Great Wall with remarkable detail. Together, they provide the positions, distances, and patterns necessary to reveal a structure so immense that it challenges not only human imagination but also fundamental assumptions about cosmic uniformity. These mapping techniques transform fleeting photons and faint galaxies into a cohesive understanding of a wall billions of light-years long, providing the framework for studying its composition, dynamics, and role in the cosmic web. The Hercules Corona Borealis Great Wall is a striking example of the universe's cosmic web, a term astronomers use to describe the large-scale organization of matter throughout the cosmos. The cosmic web is not random. Rather, it is a vast network of filaments, clusters, and voids, a three-dimensional pattern that emerges from the gravitational collapse of matter over billions of years. Galaxies are not scattered evenly through space. They form along filaments of dark matter and baryonic matter, creating interconnected structures that define the very skeleton of the universe. The Great Wall is one of the most extreme manifestations of this web, illustrating the scale, complexity, and coherence that these filaments can achieve. To understand the context, it helps to break down the components of the cosmic web. At the smallest scales are individual galaxies, each containing billions of stars. These galaxies cluster together under the influence of gravity to form galaxy groups and clusters, which themselves are connected by elongated filaments, the threads of the cosmic web. Between these filaments lie cosmic voids, vast regions where very little matter exists, sometimes hundreds of millions of light-years across. When multiple filaments align or converge over enormous distances, they can form walls, or sheet-like structures, of galaxies that stretch across billions of light-years. The Hercules Corona Borealis Great Wall is one of these walls, an extremely dense segment of the cosmic web, stretching nearly 10 billion light-years from end to end. The formation of the cosmic web is thought to be driven primarily by dark matter. In the early universe, small fluctuations in the density of dark matter created gravitational wells where gas could accumulate and form the first stars and galaxies. Over time, gravity amplified these fluctuations, drawing matter into filaments and nodes. The Hercules Corona Borealis Great Wall represents an extreme node of organization within this web, a region where many filaments and superclusters are aligned to form a continuous, wall-like feature. Without the underlying dark matter scaffolding, such a coherent and immense structure could not exist. Observationally, the Great Wall fits into the cosmic web as a dense filamentary network, connecting numerous galaxy clusters and superclusters. Unlike isolated clusters or small groups of galaxies, it is not a single gravitationally bound object in the traditional sense. Rather, it is a segment of the larger web, part of a network of filaments that define the universe's architecture. The wall's filaments serve as highways for the movement of matter, guiding galaxies, gas, and even dark matter along their lengths. Over billions of years, galaxies move along these filaments, occasionally merging in clusters, while voids expand, creating a dynamic and evolving cosmic landscape. The Great Wall also helps us visualize the hierarchical nature of the cosmic web. On smaller scales, galaxy clusters are dense knots of matter. These clusters link together via filaments to form walls like the Hercules Borealis Great Wall. On even larger scales, walls and filaments themselves form superstructures, shaping the distribution of matter across the observable universe. In this way, the Great Wall is both a product of and a contributor to the large-scale structure of the cosmos. It illustrates the continuity and coherence of matter over unimaginable distances. Another fascinating aspect is how the wall contrasts with the surrounding voids. In the cosmic web, empty regions are just as important as dense regions because they define the boundaries of filaments and walls. The Hercules Borealis Great Wall appears especially prominent because it stands out against enormous voids where galaxies are sparse. These voids create a natural contrast, highlighting the wall-like appearance when astronomers plot the positions of galaxies or gamma-ray bursts in three-dimensional space. In essence, the structure of the universe is like a cosmic lattice, with the Great Wall representing one of the largest and most striking filaments in that lattice. The Great Wall also has implications for cosmic flows and the dynamics of matter. Because gravity is the organizing force of the cosmic web, dense structures like the wall influence the motions of galaxies both within and nearby. Galaxies are drawn toward these filaments, following paths shaped by the distribution of dark matter and the arrangement of clusters. The wall, as one of the largest coherent structures, likely exerts a subtle but measurable effect on galaxy velocities over vast regions, contributing to the overall gravitational landscape of the universe. Studying the Great Wall in the context of the cosmic web also helps scientists understand the formation and evolution of large-scale structures. By analyzing its composition, distribution, and relationship to neighboring voids and filaments, astronomers can test models of how matter aggregates, how filaments align, and how voids expand. In this sense, the wall is not just a static object. It is a key feature in the dynamic, interconnected web of the universe, providing insight into the processes that have shaped cosmic structure over billions of years. Finally, its place in the cosmic web emphasizes the interconnectedness of the universe. While it is the largest known structure, it is only one filament in a vast network of walls, clusters, and voids. The cosmic web extends far beyond what we can currently observe, and the Great Wall serves as a dramatic illustration of its scale. It reminds us that the universe is not a random scattering of galaxies, but a highly organized, hierarchical system, where enormous structures are connected across unimaginable distances, all bound together by gravity and dark matter. The sheer scale of the Hercules Borealis Great Wall highlights not only the vastness of the cosmos but also the astonishing capability of human understanding and ingenuity. From our tiny vantage point on a small planet orbiting an ordinary star in the Milky Way, we have managed to detect and study a structure billions of light-years away, stretching across roughly 10 billion light-years. It is almost incomprehensible. The scale of the wall is so immense that our brains struggle to conceptualize it. Yet through observation, mathematics, and sophisticated technology, we have begun to map it, quantify its size, and understand its role in the cosmic web. To put this achievement in perspective, consider the physical distance. 10 billion light-years means the light from one end of the wall has traveled for 10 billion years before reaching us. In that time, our species barely existed, Earth itself was in its infancy, and galaxies were forming their earliest stars. Yet, using carefully calibrated telescopes and detectors, astronomers have captured faint signals from this remote region of the universe. They have used gamma-ray bursts as cosmic signposts, redshift surveys to measure distances, and computer models to reconstruct the three-dimensional distribution of matter. Each of these steps represents decades of scientific progress, technical innovation, and human curiosity focused on understanding the universe at its grandest scales. The mind-boggling aspect is not just the scale of the wall itself, but the contrast with our own existence. Our entire planet is just a tiny dot in the Milky Way, a galaxy that is itself a minute component of the Hercules Borealis Great Wall. And yet, from that tiny vantage point, we can perceive, analyze, and comprehend the patterns of billions of galaxies spread over billions of light-years. This ability speaks to the unique power of human cognition, the capacity to take observations, abstract them into models, and construct a coherent picture of phenomena far beyond our everyday experience. Moreover, the process of detecting such a structure underscores the collaborative nature of human understanding. Thousands of scientists have contributed to the observations, data analysis, and theoretical frameworks that allow us to recognize and describe the wall. Satellites like Swift and integral track gamma-ray bursts, ground-based telescopes gather redshift data, and supercomputers simulate the growth of large-scale structures over cosmic time. It is a collective human endeavor, spanning continents and decades, that has made it possible to turn a faint pattern of distant bursts into a map of the largest known structure in the observable universe. The scale of human understanding becomes even more remarkable when considering the limitations of perception. No human could ever see the wall directly. The galaxies within it are too distant and faint. Yet through indirect evidence and creative interpretation, we can infer its presence, size, and structure. This process reflects the essence of science, using limited information to extrapolate the unseen, to perceive the vastness of the cosmos from the infinitesimal vantage point of our planet. It is a profound reminder that understanding is not constrained by physical size. Intellect and technology allow humans to bridge gaps of billions of light-years. Reflecting on this, one cannot ignore the philosophical dimension. The fact that humans can detect and study a structure vastly larger than the Milky Way, something so massive that it challenges the cosmological principle, is an extraordinary testament to our curiosity and ingenuity. It is as though, from our small corner of the universe, we have developed the ability to measure, quantify, and comprehend the unimaginable, revealing patterns that are otherwise invisible and grasping the architecture of a cosmos far beyond our own lifetimes. The scale of human understanding also emphasizes the temporal perspective. Observing the Great Wall means reading signals that have traveled for billions of years, effectively seeing into the early universe. This requires not only technology but also abstract thinking, the ability to connect events across time and space, to understand that light from a distant gamma-ray burst represents a moment billions of years ago, and to use that information to reconstruct the three-dimensional structure of the cosmos. It is a form of mental time travel, enabled by science, that allows humans to perceive the universe not just in space but in cosmic time. In essence, the Hercules Corona Borealis Great Wall magnifies the contrast between the immensity of the universe and the ingenuity of human minds. From a planet smaller than the Milky Way itself, we have detected a wall that stretches across billions of light-years, mapped it using photons emitted long before humans existed, and begun to understand its significance in the cosmic web. It is a humbling and awe-inspiring achievement, one that underscores how the curiosity, creativity, and persistence of humans can illuminate even the most distant corners of the universe. Ultimately, recognizing this scale is both humbling and empowering. Humbling because it reminds us of how small we are in the cosmic scheme. Empowering because it shows that human ingenuity can perceive, study, and understand structures that dwarf not only our planet and galaxy but our entire history. The Great Wall is a monument not just of the universe's vastness, but of our capacity to comprehend it, a bridge between the incomprehensibly large and the human mind. Despite its discovery and mapping, the Hercules Corona Borealis Great Wall remains a subject of active debate within the astronomical community. While its immense size and apparent coherence are striking, some scientists question whether it is truly a single, connected structure, or whether its appearance is partly a result of observational biases, statistical anomalies, or the chance alignment of distant clusters and filaments. These debates highlight the caution and rigor that astronomers apply when interpreting data at such enormous cosmic scales. One of the primary challenges in assessing the wall's coherence is the method of detection. The structure was largely identified through gamma-ray burst mapping, which relies on rare, transient events as proxies for galaxy locations. While GRBs are effective for probing distant galaxies, they are sporadic and unevenly distributed, which introduces potential sampling biases. In regions where GRBs are sparse, apparent gaps or concentrations may exaggerate or distort the perceived structure. Some astronomers argue that this could create the illusion of a vast wall, when in reality it may consist of smaller, loosely associated clusters rather than a continuous, single entity. Another point of contention is statistical significance. The universe contains countless filaments, clusters, and voids, and the spatial distribution of these objects naturally produces regions of apparent clustering. It is possible, some researchers suggest, that the Hercules Corona Borealis Great Wall is an extreme example of random clustering, a statistical fluctuation that stands out in the observed data but does not represent a truly coherent structure. In other words, while the wall appears enormous, it might not be physically bound or dynamically connected in the way that smaller structures, like galaxy clusters, are. Further complicating matters is the sheer scale of the structure. At roughly 10 billion light-years across, the wall challenges conventional cosmological expectations, raising questions about whether structures of this size can exist coherently in the universe without violating the cosmological principle. Some astronomers view this as a clue that the wall may not be a single entity, but rather an apparent alignment of multiple structures across different distances. The difficulty lies in distinguishing between genuinely connected superclusters and filaments versus coincidental alignments projected along our line of sight. Observational limitations also play a role in the debate. Even with gamma-ray bursts, redshift measurements, and sophisticated mapping techniques, there are gaps in the data. Some regions of the sky are less thoroughly observed than others, and the faintness of distant galaxies makes it difficult to confirm whether they belong to the wall or are part of separate structures. Until more comprehensive surveys are completed, especially in the far reaches of the universe, the question of coherence remains unresolved. Despite these uncertainties, most astronomers agree that the Hercules Corona Borealis Great Wall represents a significant concentration of matter at a previously unobserved scale, even if it may not be perfectly coherent. Whether it is a single, physically connected structure or a remarkable alignment of multiple filaments and clusters, it still challenges our understanding of cosmic structure formation. The debate is therefore less about its existence and more about its interpretation and implications for cosmology. This ongoing debate also illustrates a broader theme in astronomy: the limits of observation. The universe is vast, and our perspective is confined to a single point in space and time. Determining whether an extremely distant and enormous structure is coherent or coincidental requires not only extensive data but also careful statistical modeling, simulations, and cross-verification with multiple observational methods. The uncertainty surrounding the Great Wall reflects the inherent difficulties of studying structures at the very edge of human detection capabilities. Some astronomers are hopeful that future observations will clarify the issue. Upcoming large-scale surveys, deeper redshift mapping, and more sensitive gamma-ray observatories could provide additional data points, allowing scientists to test whether the wall structure is truly connected across its entire length. Meanwhile, theoretical models can explore whether cosmic evolution naturally allows for structures of this size or if alternative explanations are necessary. Until then, the Great Wall remains a fascinating enigma, both a discovery and a puzzle that provokes questions about the universe's organization on the largest scales. In essence, the debate over the Hercules Corona Borealis Great Wall highlights the intersection of observation, theory, and interpretation in modern cosmology. It reminds us that even as we push the boundaries of what we can detect and understand, uncertainty remains a central part of scientific inquiry. The wall may ultimately be redefined in terms of its physical connectivity, but whether coherent or coincidental, it has already reshaped our conception of cosmic scale and challenged our assumptions about the limits of structure formation in the universe. The Hercules Corona Borealis Great Wall is currently the largest known structure in the observable universe, but our understanding of it is still evolving. Much of what we know comes from indirect observations, statistical analysis, and gamma-ray burst mapping. As technology advances and new telescopes and surveys come online, astronomers anticipate that our knowledge of the wall, and potentially even larger structures, will become far more detailed and precise, possibly refining, or even challenging, existing models. One of the most promising instruments in this effort is the James Webb Space Telescope, JWST. Unlike previous space telescopes, JWST is optimized for infrared observations, allowing it to peer through cosmic dust and detect extremely faint and distant galaxies. Since the Hercules Corona Borealis Great Wall lies roughly 10 billion light-years away, many of its constituent galaxies are faint and redshifted, their light stretched into the infrared range. JWST sensitivity enables astronomers to observe these galaxies directly, rather than relying solely on gamma-ray bursts as markers. By capturing images and spectra of previously unobservable galaxies within the wall, JWST can refine measurements of galaxy distribution, cluster density, and redshift, providing a more accurate three-dimensional map of the structure. In addition to JWST, next-generation ground-based surveys are expected to revolutionize our understanding of cosmic structures. Projects like the Vera C. Rubin Observatory and the Euclid Space Telescope will carry out massive surveys of galaxies and dark matter across large portions of the sky. These surveys will use a combination of photometric and spectroscopic data to measure redshifts for millions or even billions of galaxies, significantly increasing the resolution and completeness of large-scale structure maps. For the Hercules Corona Borealis Great Wall, this means that astronomers could determine whether the wall is truly coherent, or whether it is composed of multiple overlapping filaments and clusters seen in projection. Upcoming radio surveys, such as those conducted with the Square Kilometre Array, SKA, will further enhance our understanding. By mapping hydrogen gas and other components of the intergalactic medium, radio observations can reveal filamentary structures invisible in optical light. This adds another layer of detail, showing how the wall is connected not just by galaxies but by gas and dark matter. Such observations could clarify how matter flows along filaments, how clusters interact gravitationally, and how voids frame these enormous structures. Another exciting avenue is the use of multi-messenger astronomy, combining gamma-ray, X-ray, optical, and gravitational wave data. For example, the detection of neutron star mergers through gravitational waves could provide additional markers of galaxy locations at extreme distances, complementing gamma-ray burst mapping. By integrating these different signals, astronomers will obtain a more complete and nuanced picture of the wall and its place in the cosmic web. The implications of these future discoveries extend beyond simply mapping the wall more accurately. They may also help resolve ongoing debates about its coherence and significance. If high-resolution surveys confirm that the wall is indeed a continuous, connected structure spanning 10 billion light-years, it would reinforce its status as a unique anomaly in the observable universe, compelling theorists to rethink models of structure formation and potentially challenging the cosmological principle. Conversely, if more detailed observations reveal that the wall is a superposition of smaller, loosely connected filaments, it may alleviate some of the tension with current cosmological models, showing that extreme alignments can occur without violating fundamental principles. Moreover, these observations may reveal even larger structures beyond the Hercules Corona Borealis Great Wall. As our telescopes probe further into the universe and detect galaxies at greater distances, we may discover walls, filaments, or clusters that surpass the current record holder. The wall might eventually be seen as one segment of an even grander cosmic network, highlighting the hierarchical and interconnected nature of the universe on scales far beyond what we currently comprehend. The combination of new instruments, deeper surveys, and sophisticated modeling promises a transformative decade for cosmology. The Hercules Corona Borealis Great Wall will likely remain a focus of research, both as a laboratory for studying large-scale structure and as a benchmark for testing the limits of our understanding of the universe. With each new observation, astronomers can refine estimates of galaxy density, map intergalactic gas, measure dark matter distributions, and study the wall's formation and evolution over cosmic time. In summary, future discoveries powered by JWST, Rubin Observatory, Euclid, SKA, and multi-messenger astronomy have the potential to clarify, refine, and possibly challenge our understanding of the Hercules Corona Borealis Great Wall. These advances will not only reveal more about this specific structure but also expand our knowledge of the cosmic web, the processes that shape it, and the ultimate limits of large-scale structure in the universe. The next decade of astronomy promises to transform the Hercules Corona Borealis Great Wall from a distant curiosity into a fully characterized cornerstone of our understanding of the cosmos. The Hercules Corona Borealis Great Wall is not just a scientific marvel, it is also a profound philosophical mirror, reflecting the enormity of the cosmos and our place within it. To grasp that a single structure stretches across 10 billion light-years, encompassing billions of galaxies, each containing billions of stars, is to confront the sheer scale of the universe, a scale so vast that human intuition struggles to comprehend it. Yet, from our small vantage point on Earth, we can observe, measure, and begin to understand this gargantuan formation. This juxtaposition of human fragility and cosmic immensity invites reflection on both humility and wonder. On one level, the Great Wall underscores the insignificance of our everyday concerns in a universe of incomprehensible size. Our planet, our solar system, even our galaxy, are minute specks compared to the scale of the wall. In the context of the cosmic web, the Milky Way is just one tiny dot along a filament that stretches billions of light-years, which itself is only one piece of an interconnected network of walls, filaments, and voids. It is a humbling reminder that our existence is fleeting and fragile in the grand narrative of the cosmos. Yet, this awareness does not diminish human significance. Rather, it places our curiosity and intellect into a remarkable light. From our tiny planet, We are capable of discerning structures that dwarf our imagination, reconstructing the universe's architecture across billions of years and light-years. The discovery of the Great Wall also raises questions about perspective and perception. Humans tend to measure significance by proximity, familiarity, and scale. A mountain may feel immense, an ocean infinite, but both pale in comparison to the vast filaments of galaxies spanning billions of light-years. Recognizing this challenges us to expand our conceptual horizons, to think in terms of cosmic time, cosmic distance, and cosmic structure. It encourages a mindset in which human concerns coexist with awareness of our place within a much larger, interconnected universe. There is also a philosophical dimension in the relationship between observation and understanding. The Great Wall exists independent of human perception. It was present in the universe long before we evolved, and its light only reached us billions of years later. Yet, through ingenuity, reasoning, and collaboration, we can detect, map, and study it. This ability to reach across space and time with knowledge is uniquely human, demonstrating that while we may be small physically, our minds possess the capacity to connect with the cosmos on a scale that is otherwise unimaginable. In a sense, the Great Wall reflects both the grandeur of the universe and the extraordinary nature of human cognition. The immensity of structures like the Hercules Borealis Great Wall also invites reflection on cosmic humility and awe. These feelings have long been central to philosophy and science alike, from ancient stargazers who looked at the night sky in wonder to modern astronomers charting billions of galaxies. The Great Wall amplifies that sense of awe, showing us that the universe is structured in ways that are far beyond the human scale and yet accessible to human inquiry. It compels us to confront questions about meaning, place, and purpose, not in the sense of cosmic significance, but in the sense of awareness, that we exist in a universe of immense complexity, beauty, and mystery. At the same time, the Great Wall can inspire optimism about human capability. Despite our small size, our ability to detect a structure of this magnitude demonstrates that knowledge and curiosity can overcome physical limitations. It shows that intelligence, observation, and collaboration can bridge vast distances and timescales, enabling us to grasp the patterns of the universe in ways that would have seemed impossible just a century ago. The Great Wall becomes, in this light, not just a cosmic structure, but a symbol of the potential of human understanding. Finally, contemplating the Great Wall encourages us to think in terms of interconnection. Just as galaxies are linked by filaments in the cosmic web, human beings are connected by networks of thought, observation, and communication. Observing a structure where matter is woven across billions of light-years can inspire recognition of patterns, relationships, and coherence, both in the universe and in our own lives. It challenges us to find meaning in observation, inquiry, and the pursuit of knowledge, even when the scale of the cosmos dwarfs individual existence. In sum, the Hercules Borealis Great Wall invites a profound philosophical reflection. It challenges human perception, evokes awe at the scale of the universe, inspires humility in the face of immensity, and yet simultaneously celebrates the power of human understanding. It shows that we are both tiny and remarkable, small in physical scale but capable of perceiving and contemplating structures billions of times larger than ourselves. It is a reminder that the universe is vast, intricate, and awe-inspiring, and that our ability to explore it intellectually is itself a testament to the remarkable potential of human thought. As we reach the culmination of this journey through the cosmos, the Hercules Borealis Great Wall stands as a monument to the universe's grandeur and complexity. It is not merely a collection of galaxies or clusters. It is a staggering testament to scale, stretching roughly 10 billion light-years across, dwarfing every familiar cosmic landmark we know. Even the Milky Way, immense though it seems to us, is a mere speck in comparison, about 100,000 light-years wide, emphasizing how inconceivably large and intricate the universe truly is. The Great Wall challenges our very notion of what can be considered big. For centuries, humans defined the limits of scale in terms of the Earth, then the solar system, then the galaxy. But the Hercules Borealis Great Wall pushes the boundaries beyond imagination, forcing us to reckon with structures that occupy a significant fraction of the observable universe. Its discovery reminds us that the cosmos is far more vast and intricate than our minds can fully comprehend, a reality where light itself must traverse billions of years to convey even the faintest hints of distant matter. Yet what makes the wall truly remarkable is not just its size, but the way it embodies the universe's hidden order. It is part of the cosmic web, a network of filaments, clusters, and voids that demonstrates the universe's hierarchical structure on unimaginable scales. Its existence speaks to the power of gravity, the evolution of galaxies, and the mysterious scaffolding provided by dark matter, an elegant, interconnected pattern stretching across time and space. The Great Wall is a symbol of cosmic architecture, showing that even in a universe that appears chaotic, there is structure, coherence, and beauty. It is also a testament to human ingenuity and perseverance. From our small vantage point on Earth, we have detected, mapped, and begun to understand a structure so vast that it defies conventional comprehension. Through gamma-ray bursts, redshift surveys, and the combined efforts of thousands of astronomers across decades, humanity has glimpsed a piece of the universe that existed billions of years ago, long before our planet formed. The wall embodies both the universe's immensity and the remarkable capability of the human mind to perceive and explore it. As we reflect on the Hercules Corona Borealis Great Wall, it is impossible not to feel a sense of awe and humility. It is a reminder that the universe is not only bigger than we imagined, but full of wonders that continue to challenge our understanding. Each discovery expands the horizon of what we thought possible, showing that even structures that seem unimaginable today may be mapped, studied, and contextualized through the ingenuity of observation and analysis. The Great Wall is both a physical and intellectual milestone, a bridge between the infinite cosmos and the human capacity to comprehend it. Finally, the Hercules Corona Borealis Great Wall inspires a sense of perspective. In a universe filled with vast voids, luminous galaxies, and interconnected filaments, our place may seem small, yet our ability to explore, understand, and wonder is immense. The wall redefines the biggest, not merely in spatial terms, but in its capacity to expand our imagination, challenge our assumptions, and remind us that the universe has no shortage of mysteries waiting to be discovered. So as we close this journey, the Great Wall stands as a testament to cosmic grandeur and human curiosity alike. It is a reminder that beyond the stars we see, beyond the galaxies we know, and beyond the filaments and clusters that span the cosmos, there exists a universe of limitless scale, profound complexity, and endless wonder, and that every new discovery, like the Hercules Corona Borealis Great Wall, brings us a little closer to understanding our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.